Welcome to submodule 1 of 3 of our training on extended reach drilling, or ERD. In this session, we'll define what ERD wells are, examine key examples, and explore both the benefits and the challenges. We'll also review design and operational considerations that distinguish ERD from conventional wells. Let's begin with the module objectives. By the end of this submodule, you'll be able to explain the industry definition of an ERD well. This includes understanding how parameters such as measured depth versus true vertical depth, displacement ratios, and industry indices determine ERD classification. Second, you'll be able to list the benefits of ERD wells. These range from enabling satellite field development and reducing subsea infrastructure to improving environmental performance. Third, we'll cover the factors that limit ERD step out, such as torque and drag, hole instability, and fluid interactions. Next, we'll start with definitions and examples. Let's begin with how extended reach drilling is defined and illustrated with examples. An extended reach well is typically defined by the ratio of measured depth to true vertical depth. When that ratio exceeds 2:1, we enter ERD territory. For example, if a well has a vertical depth of 10,000 feet, but a measured depth of more than 20,000 feet, it qualifies as ERD. Other definitions are also recognized. One is when displacement over TVD is greater than or equal to 2. Another involves the drilling difficulty index, which is used to characterize well complexity. Some classify ERD when inclination angles exceed about 63 degrees, reflecting the transition to high-angle drilling. ERD can also be defined pragmatically. Any well that approaches the limits of what is technically achievable by the industry or what the contracted rig can handle may be classed as ERD. These definitions are important because they establish the scope of engineering and operational challenges that come with ERD, guiding us on when special practices are required. Here we see some of the standout examples of extended reach drilling. The Chavo Z42 well, drilled by Exxon Neft Gas Limited offshore Sakhalin, Russia, remains one of the longest ERD wells, with a measured depth of over 41,000 feet and a horizontal departure of more than 38,000 feet. These numbers highlight the scale of what ERD technology can achieve. Other significant examples include the Sakhalin-1 project, where 25 wells achieved MD/TVD ratios between 3.9 and 6.9, setting industry benchmarks. Maersk Oil Qatar pushed the limits further, with the Al Shaheen field achieving a ratio of 11.1, which is remarkable by any standard. BP's Witch Farm project in the UK achieved ratios of around 6.6 to 6.9, while Total in Argentina drilled the Cullen Norte No. 1 with a ratio of 6.7. Offshore California, ExxonMobil's Santa Ynez unit achieved a ratio of 5.36. These examples demonstrate that ERD wells are not isolated cases, but a proven technique across multiple basins and operators. On the next slide, we'll continue with further examples. This slide continues with additional examples of extended reach wells. What's clear from these projects is that ERD has been adopted worldwide, from offshore developments in harsh Arctic environments to mature onshore fields where maximizing reach is essential. These wells illustrate both the technical capability of drilling systems and the strategic value ERD brings. For example, long horizontal step-outs allow operators to reach reservoirs that would otherwise require costly offshore infrastructure or multiple platforms. By drilling from a central pad or shoreline location, development becomes more efficient and environmentally responsible. Each of these case studies contributes to the industry's body of experience, pushing the limits further with every successful project. The key takeaway is that ERD is not only about records, but about solving field-specific challenges, whether it's extended reach from shore, developing marginal fields, or improving recovery. Now let's focus in on a specific case, the Witch Farm field in the UK, which is often cited as one of the most successful applications of ERD. The Wych Farm oil field in the UK is a classic example of extended reach drilling used to great effect. Located onshore in Dorset, the field extends offshore beneath environmentally sensitive areas and the English Channel. ERD enabled operators to access these offshore reservoirs from land, avoiding the need for offshore platforms and subsea infrastructure. This reduced costs and minimised environmental impact while still achieving high recovery. The project pushed technical boundaries, with wells reaching measured depths well over 30,000 feet and horizontal displacements of more than 6 kilometres. Managing torque, drag and hole cleaning at those lengths required significant innovation in well design and drilling practices. The Wych Farm project demonstrated the practicality of ERD not just for record setting, but for economic and environmental reasons. It remains a benchmark for ERD field development worldwide. On the next slide, we'll look at a second example from Wych Farm that further highlights the benefits of this approach. Continuing the example from Wych Farm shows how the project evolved as experience grew. With each successive well, operators refined their understanding of hole cleaning, torque and drag, and casing design for extended lengths. The later wells achieved even greater displacements, proving that consistent success in ERD is possible with the right planning and execution. Importantly, these wells demonstrated how ERD can be scaled from a few extended wells at the start to an entire development strategy built around long step-outs. The Wych Farm case also illustrates the value of ERD for environmental stewardship. Sensitive coastal and marine environments were protected by eliminating offshore structures, while still accessing reserves. In summary, Wych Farm shows that ERD is not just technically feasible, but operationally sustainable and economically advantageous. Next, we'll broaden our view and consider the general benefits ERD wells bring to field development strategies. Extended reach drilling wells bring several important benefits despite their higher cost and technical complexity. First, ERD can reduce the need for subsea equipment and pipelines. By drilling long step-outs from a central facility, we avoid installing subsea trees and flow lines, which reduces capital expenditure and operational risk. Second, ERD wells enable satellite field development. Marginal or stranded reservoirs that are uneconomical to develop with standalone platforms can be reached cost-effectively from existing facilities. Third, ERD makes it possible to develop nearshore fields from onshore. This reduces offshore footprint, improves logistics, and eliminates the need for offshore manned installations. Finally, ERD can minimize environmental impact by drilling from pads, either onshore or clustered offshore. Operators reduce surface disturbance, protect sensitive environments, and meet regulatory expectations. These benefits combine to make ERD an important part of many modern development strategies, especially where minimizing infrastructure and maximizing efficiency are priorities. Next, we'll balance these advantages by reviewing the limiting factors that constrain ERD step-outs. While ERD wells offer great benefits, they are limited by several technical and operational factors. Hole instability is a major issue. The longer the well bore, the greater the chance of mechanical failure, sloughing shales, or collapse. Time exposure compounds this, as formations weaken the longer they remain open. Geomechanical interactions and adverse pressure differentials can also destabilize the hole. Drilling fluids play a role too. Sometimes interactions between mud and formation lead to swelling clays or compatibility issues. Drag is another limiting factor. Over long distances, the drill string can experience so much friction that it fails to reach bottom. This is tied to cumulative hole length and the dogleg severity along the path. Finally, torque capacity of tubulars sets a hard limit. Once torque approaches the design threshold of drill pipe or connections, additional step-out becomes unsafe. Together, these factors determine the practical maximum reach of ERD wells. On the next slide, we'll see how this shrinking margin of error is represented graphically. This chart illustrates how the margin for error decreases as reach increases. On the x-axis, we see throw, the horizontal displacement, while the y-axis shows true vertical depth. The key takeaway is that as wells extend further horizontally, tolerance for error narrows. Small deviations in trajectory, drilling parameters, or hole condition can quickly escalate into major operational problems. At shorter reaches, there is flexibility. Issues like drag or torque can be managed with adjustments. But as the throw increases into the tens of thousands of feet, even small inefficiencies can cause failures in hole cleaning, stuck pipe, or loss of circulation. This shrinking margin of error underscores why ERD wells demand meticulous planning and execution. Every element, BHA design, drilling fluid properties, tripping practices, must be optimized to minimize risks. On the next slide, we'll look at the key factors that must be considered when planning and executing ERD wells. When planning ERD wells, there are several critical factors that must be addressed. When planning and executing extended reach wells, we must consider a broad range of factors that extend beyond conventional well design. These considerations are critical because the margin for error in ERD operations is much smaller than in standard wells. The first priority is hole cleaning. In long, high-angle sections, cuttings tend to settle on the low side of the hole, forming beds that are extremely difficult to remove. Without proactive cleaning strategies, drag and torque will escalate quickly, leading to stuck pipe. This ties directly into equivalent circulating density management. Long intervals and high flow rates can drive ECD above fracture pressure, causing losses, or drop it below pore pressure, inducing influxes. Balancing hydraulics is essential. Next, BHA and bit design strategies must be optimized for long laterals. The assembly needs to be durable, minimize vibration, and provide steerability while keeping torque within limits. Tripping practices must also be carefully controlled. In horizontal wells, wiper trips don't clean the hole, and excessive backreaming risks destabilizing the wellbore. Wellbore instability and mud properties must be addressed in tandem. Inhibitive mud systems, correct rheology, and chemical stability are all vital. Drilling parameters such as weight on bit, RPM, and flow rates must be optimized to reduce mechanical risk and improve efficiency. From a construction perspective, casing design and running procedures are more demanding. Long strings must be run with minimal drag, requiring reaming tools, centralization, and careful hydraulics. Cementing in long, deviated sections is also more challenging, requiring good mud removal and zonal isolation techniques. Finally, ERD wells involve greater logistical complexity, equipment requirements, and cost visibility. Rigs must handle long tubulars, heavy torque, and advanced tools. ERD projects are high profile, so operational efficiency and safety performance are under close corporate and sometimes governmental scrutiny. Altogether, these factors demonstrate that ERD wells demand meticulous planning, specialized technology, and disciplined execution. Highlighted in red are the most critical parameters that require meticulous planning and control. These include hole cleaning and tripping, as well as wiper tripping practices. This is because these have the greatest statistical risk of non-productive time exposure. Hole cleaning is one of the most critical challenges in extended reach drilling. In ERD wells, the cuttings transport mechanisms are significantly more complex compared to those in vertical or low-angle wells. At high inclinations, cuttings tend to settle on the low side of the hole, creating beds that are difficult to remove. Circulation times are longer than in low-angle wells, meaning it takes more time to bring cuttings to surface. This delays feedback and increases the risk of build-up. Another factor is that mud properties optimized for vertical wells are not effective in high-angle holes. Viscosity, density, and gel strengths must be adjusted to suit the trajectory. Interestingly, hole cleaning sweeps, commonly used in vertical wells, are often counterproductive in ERD. They may not effectively mobilize cuttings beds, which can disturb wellbore stability. In short, hole cleaning becomes a top operational priority in ERD. Poor cleaning leads quickly to pack-offs, stuck pipe, or excessive drag. Next, we'll move to another critical operational issue in ERD wells, tripping and wiper tripping practices. Tripping practices take on a new level of importance in extended reach wells. In fact, correct tripping practice is often the single most critical operational issue for ERD. The risk of stuck pipe is much higher in horizontal or high-angle sections than in vertical intervals. A key point is that the meaning of wiper trips is different in ERD. In vertical wells, wiper trips help clean the hole, but in horizontal wells, the BHA does not effectively move cuttings back to surface, so wiper trips don't achieve the same purpose. Moreover, repeated trips can actually make things worse. They may induce shale instability due to cyclical stress or fatigue the wellbore. Another practice to avoid is back reaming. While sometimes used to address tight spots, it is time-consuming and carries high risk. Back reaming can create self-inflicted wellbore instability, cause high vibration levels, accelerate casing wear, or even lead to lost returns. In summary, tripping in ERD wells must be deliberate, controlled, and minimized. Now, let's wrap up this submodule by reviewing the objectives and confirming what we've covered. Let's revisit the objectives we set at the beginning of this submodule and review how we've met them. First, we aim to define the concept of extended reach drilling. We established that ERD wells are typically characterized by a measured depth to TVD ratio of 2 to 1 or greater, or by pushing the limits of rig or industry capability. Second, we looked at the benefits of ERD wells. We saw how they reduce subsea infrastructure, enable satellite field development, make nearshore resources accessible from land, and minimize environmental impact. Third, we reviewed the factors that limit ERD step-out, including hole instability, time exposure, drag, torque capacity, and fluid-related challenges. This concludes submodule 1 of 3 on extended reach drilling. Please proceed to the quiz to check your understanding of the material. Thank you for your attention and engagement throughout this session, and I look forward to continuing with you in the next part of the training.